In this example, we'll be once again using the second derivative test to determine the local max and mins. Now you'll notice this function here would require, when we take the first derivative, to use a product rule. We don't have to use a product rule. I could theoretically distribute that x to the 1/3 into the problem and make it something entirely different so that the derivative is easier for us to use. But for the sake of practice, I'm going to go ahead and keep it as it is and take the derivative using the product rule. So very carefully, the product rule states I'm going to take the derivative of the first function, which is 1/3 x to the negative 2/3, times the second function left unchanged, plus, leaving the first function left unchanged, times the second derivative, or the second function in terms of its derivative, which is just 1. So that provides me with a function I can work with here. And be very, very careful with this. Again, it's going to get relatively uncomfortable in terms of the values that we have in here. This negative exponent, I'm going to want to manipulate so that it is no longer a negative exponent. Again, every time that we see those negative exponents, things are going to get a little bit more difficult for us. But this seems like it's the most appropriate way to deal with it at this point. Now, my second detail that I'm going to want to note here is that I need to go ahead and find my critical points of this function. The critical points will once again allow me to find out where there could be a local max or min. So I need to go ahead and determine where there's a does not exist case or an equal to 0 case. Well, the most appropriate way to do this is to take this entire function and make it one giant fraction. So I'm going to go ahead and do that very carefully by manipulating the functions that I'm already given. You'll notice that if I do this very carefully, this denominator is what I need to have in common over here. So that's what I'm going to do. On top and bottom, I'm going to multiply by 3x to the power of 2/3 over 3x to the power of 2/3. Now, conveniently enough, and in most cases this is how it works out, this bottom is not going to multiply by anything, so it's just going to be multiplied by 1. And this top here will actually allow us to multiply these two x's together, giving us simply x to the 1, because again, when I multiply two of the same base, I add those exponents. Again, 1/3 plus 2/3 is 3/3, which is 1. So that gives me with x minus 4 plus, on top I'm going to have 3x, all divided by that 3x to the power of 2/3. This ends up giving me 4x, again, 3x plus 1x, minus 4, divided by 3x to the power of 2/3. So again, this here is the function that we have for the first derivative. Identifying that this is the first derivative function, I can very easily then say, where does the derivative not exist? That's where the bottom equals to 0, which actually provides me with x equals to 0. And where does the top equal to 0? Because that provides me where, again, the derivative itself is equal to 0. This gives me x is equal to, adding the 4 and dividing by 4, 1. So now I have two locations that are potential critical points, which are potential local max and mins. Now I will take these values and I'm going to go ahead and identify what the second derivative function is, because again, this is the second derivative test. So now I'm going to have to take the derivative of this new function, which again, we could utilize a product rule with a negative exponent, but I'm going to go ahead and keep it as it is and use a quotient rule to simplify it a little bit better. Keep in mind, my goal is not to make this as complicated as possible. My goal here is to be able to plug 1 and 0 into the derivative, or the second derivative in this case. So when I go ahead and do that, this is going to provide me with, I'm going to go ahead and very carefully take the derivative of the top, which is 4, leaving the bottom unchanged, minus the derivative of the bottom is going to be 3 times 2/3 x to the power of a negative 1/3, and then the top left unchanged, 4x minus 4. This is all divided by the bottom, 3x to the power of 2/3 squared. Now you'll notice here as we get more and more complicated versions of these problems, the skills that you have in terms of dealing with exponents is going to have to be relatively solid. So please make sure you practice dealing with these exponents in terms of negatives and positives. So now the next thing I'm going to do is I'm going to go ahead and try and clean this up just a little bit so it makes it easier for me to plug values in. The first thing I'm going to identify is that this here doesn't need to worry. I'm going to go ahead and just multiply that together. So that's no big deal. Next thing I'm going to notice is here this 3 and this 3 in the denominator of this second piece can cancel each other out, leaving me with simply 2 times x to the power of negative 1/3. So that's going to give me 2x to the negative 1/3 times 4x minus 4, all divided by 3x to the power of 2/3 to the power of 2. Now, the last piece I'm going to simply worry about is plugging in 0. Now you'll notice that the second derivative doesn't exist at 0. There's a D&E case at f double prime of 0, which means that this thing could do all sorts of different things. It really just means that the second derivative does not have a nice concavity at that point, which means that we're actually probably going to have to use the first derivative test on 0 all over again. Again, because that situation gives us a DNE or a 0, we're going to have to go ahead and try a different method to determine if that's a max or a min. For 1, when I go ahead and plug 1 into this function, things work out quite nicely. Again, this is the cube root of 1 squared, which is just 1. So I'm going to have 12 minus, same situation more or less here, 2 times 4 minus 4, which this ends up all just being 0, all divided by 3 squared. Again, be very careful with 3 times 1 to the power of 2/3. 1 to the power of 2/3 is simply 1. 3 times 1 is 3. 3 squared is 9. So I'm going to end up with something that looks like 12 divided by 9. In this case, this is a positive number, and because this is positive, it means that the second derivative is positive, which implies that f of x is concave up. It being concave up, again, looks something like this, which means that we're going to have a local minimum at that point. So, by the second derivative test, there is a local minimum at x equals 1 with a value of f of 1 equaling 2. Again, we plug 1 in here. I'm going to have 1 times negative 3, so simply a negative 3. And that, again, is going to give me my local minimum. Again, for 0, we're going to want to go ahead and try and plug this in to the derivative function on either side. So again, 0, 1, I want to use 0.5 as a test value, and I'd probably going to want to go ahead and try and use negative 1. This is, again, the first derivative test. Those are the test values I'm going to pick. Again, I don't need to worry about over here because, again, it didn't ask me for increasing and decreasing. It simply asked where the max or mins, and I've already identified that x equals 1 is a local minimum. So now when I plug in negative 1 to the derivative function somewhere down here, simplest form possible, I'm going to end up with a negative value on top and a negative value on the bottom, which provides me with a positive. And when I plug in 0.5, very carefully, 0.5, on top I'm going to get a negative, and on the bottom I'm going to get a positive, so that's going to be a negative. So that means that this is what the derivative function is doing, which means that the function itself, f of x, is going to be increasing and decreasing. And since 0 is a value that exists on this graph, that location right there is going to be a local max. So based on the first derivative test, I will say that at x equals 0, there is a local maximum of the value f of 0, which ends up being 0. And that, again, is your conclusion to that problem based on the second derivative test, which forces us to use the first derivative test.